everyone, this is problem number 3 on problem set number 1. A blacksmith cools a 1.2 kilogram chunk of iron, initially at 650 degrees Celsius, by trickling 15 degrees Celsius of water over it. All of the water boils away and the iron ends up at 120 degrees Celsius. How much water did the blacksmith trickle over the iron? Okay, let's start with the givens of the problem. So we have, that's kind of, okay, that's fine. Okay, so we have the mass of iron that is given at 1.20 kilograms. We have the initial temperature of iron, so T iron initial, at 650 degrees Celsius. Okay, and that chunk of iron is cooled by trickling 15 degrees Celsius of water over it. So we know that the initial temperature of water, TW naught, is equal to 15 degrees Celsius. All of the water boils away and the iron ends up at 100 degrees Celsius. So T iron final is equal to 120 degrees Celsius. Okay, how much water did the blacksmith trickle over the iron? So what's the mass of water? Okay, we know that all of the water boils away, right? That's kind of a key thing here. So what does that mean? That means whatever MW was initially experienced a phase change and eventually became steam, right? So M steam. That's what happened to the M water. So they're equal, so we'll just call it MW for simplification purposes. But we know there was a phase change. That is very important. Okay, so we will solve this by using the formula, and I think it was 17.6 calorimetry. And that is that the sum of all heat transfer equals 0. Okay. If you guys haven't seen the video I posted with important formulas for chapter 17, check that out. Okay. So in calorimetry, the sum of all heat transfer is equal to 0. Yeah? So that's denoted by the summation of Qi is equal to 0. So what I explained in the video, but I will explain again, this consists of two things. The first one is Qi is equal to MC delta T, or T final minus T initial. Okay? And the other Q, or heat transfer, Qi, is equal to plus or minus M F plus or minus M L V. Okay? So Q consists of the mass. Let's change color. So we got the mass multiplied by the specific heat and multiplied by the change in temperature. Okay? But that is only the heat transfer required, that is just the heat transfer when it comes to temperature change within the same phase. Okay? So this guy is only for temperature change or heat transfer associated with temperature change within the same phase. Okay, but as we saw, we also experience phase change in this problem when all the water boils away and is converted to steam, right? So we know that we'll have to use one of these equations, and these equations are used when there is phase change. So you're just going to have to choose between the latent heat of vaporization when you deal with something between solid or between liquid and gas, okay, and the latent heat of fusion right here when you deal with something between solid and liquid or liquid to solid, right? Okay. Oh, and obviously the plus or minus, that depends on if heat enters the system or leaves the system, right? Positive, Q is positive when heat enters the system and is negative when heat leaves the system, right? Okay. So, with that being said, that was just a little review. Let's go back. So in this problem, okay, delta or summation of heat transfer is equal to mass of the iron times the specific heat of the iron. I feel like I'm writing too big. Multiplied by the final temperature of the iron, Tf iron, minus T not iron. Okay, I know I wrote it this way and this way, but you know what I mean. All right, I'll change it just because I have OCD. Okay, so T iron final minus T iron initial. Okay, plus the mass of water times the specific heat of water times the final temperature of water minus, I did it again. So minus the final temperature of water minus the initial temperature of water. Okay? And because there is a phase change associated with this problem, I will have to use one of these guys for water. So let's see what the state is. The state goes from water to steam, right? Water to steam. So I know I'm going to have to use this guy, the latent heat of vaporization. So it's going to be plus, because we're going from water, liquid, to steam, so temperature is increased, or heat is added to the system. So we've got M of water, mass of water, times latent heat of vaporization of water. Okay? Here. So this is the temperature change. This is the heat transfer associated with the temperature change for iron. Temperature change for water. And this guy is the phase change when we go from water to steam, right? You might ask, why doesn't iron have one of these equations or one of these formulas in our equation? And that is because the initial temperature of iron is at 650 degrees and the final temperature of iron is at 120 degrees Celsius. And the iron doesn't change it doesn't experience a phase change. It's still a solid at both temperatures, initial and final. So that's why there's no phase change formula associated in this problem for iron. Okay. Oh yeah, and this, right? Like we said, in calorimetry, the sum of all heat transfer equals 0. So this is all equal to 0. There you go, equal to 0. All right. I guess I just kind of want to show this just for clarity. If this is something you guys already know, feel free to skip. So temperature, heat added. Okay. This is for water. So solid, that's ice, liquid, water, and gas, that's steam, right? This is the solid to liquid melting point. This is the boiling point. Okay, and this is for water. So melting point for water is 0 degrees Celsius. 0 degrees Celsius. And boiling point for water is 100 degrees Celsius, right? And we know initially our T naught is somewhere here at 15 degrees Celsius for water. That's given in the problem. And it eventually experiences phase change, so it turns into steam, and it ends up somewhere right here, right? I don't know what, somewhere there. But anyways, it does experience phase change here at this point when it boils, right? So that's why we've got this guy added for water. Okay, that was just a little side note. Now back to the problem. Okay, so we have mass of iron times specific heat of iron. Actually, I'm not gonna rewrite all of that because it's right here. Let's see, what's our given? What do we know? We know this is given. Okay, we know that. This is given. This is given. Mass of water, we don't know that. This is what we want to find out. T water final. This one is technically not given, but we know that in order for phase change to occur, this is actually 100 degrees Celsius right here. That's boiling point, right? That's where phase change between liquid to gas occurs for water at that temperature. Initial temperature of water, that's also given. Mass of water, we don't know. That's what we're trying to find out. Okay, and as far as these guys, the specific heat of iron, specific heat of water, and latent heat of vaporization of water, I found that from Google. You guys might get that as a given on the test, or maybe a little chart to figure that out. Anyways, according to Google, the specific heat of iron is equal to 0.47 times 10 to the 3 joules over kilogram times Kelvin. For water, specific heat is 4.19 times 10 to the 3 joules per kilogram times Kelvin. And the latent heat of vaporization for water is 2,256 times 10 to the 3rd joules per kg. Again, these guys you could find on Google or might be given to you. Okay, so now we've got that, we've got that, we've got that. We have everything we need in this equation to solve for mass of water. So let's just do some plug and chug. Oh, there you go. Okay, so actually before we do the plug and chug, let's do the algebra first on this guy. So, okay, So I know that M, water, temperature change of water plus mass water, latent heat of vaporization of water is equal to negative mass of iron, specific heat of iron, times temperature change of iron. T iron, not. Okay, sorry, I was trying to make this as neat as possible. Okay, right? That we know. Okay, so let's bring this down. We'll just factor out mass of water. So we get, actually, should utilize space, right? So we factor out mass of water. We have specific heat of water times final temperature of water minus initial temperature of water plus latent heat of vaporization of water is equal to negative mass of iron, specific heat of iron times change in temperature of iron. Okay. So then mass of water is equal to negative minus T iron naught divided by specific heat of water, temperature change of water, plus latent heat of vaporization of water. Okay. Again, we have everything we need to find mass of water, so at this point it's a plug and chug kind of thing. Mass of iron, that was given at 1.2 kilograms. Don't forget the negative right there. So 1.20 kilograms. That's negative, yeah? Okay, I'm going to erase that because I can't see the negative. Okay, that's negative, okay? Negative, okay? Equals. Specific heat of iron, that's 0.47 times 10 to the third joules per kg times Kelvin. Okay, and temperature change for iron, we've got it here and here. Okay, so 120 minus 650 Celsius. So 120 degrees Celsius minus 650 degrees Celsius divided by specific heat of water, that is 4.19 times 10 to the third joules per kilogram times Kelvin. And that is multiplied by the change of temperature in water. And again, remember, for temp change of water, let's use the highlighter. For temp change of water, the final temperature of water, in order to experience phase change, what is it? The boiling point from liquid to gas, that's 100 degrees Celsius. So this guy, that is 100 degrees Celsius, the boiling point of water, when it changes from water to steam. And we subtract that by the initial temperature of water, which is here, 15 degrees Celsius. So 15 degrees Celsius. 15 degrees Celsius. And add the latent heat of vaporization for water right here. That's 2256 times 10 to the 3 joules per kg. Okay, so that is the mass of water. And if you plug that in a calculator, you're going to get that the mass of water is equal to how much water did the blacksmith trickle over the iron? That is equal to 0.114 kilograms. There you go. Okay, so hopefully that helps